All right, let's take a look at these two compounds. And all we're trying to do is identify the functional groups. So we'll start with the compound on the left. I'll give you a clue. There's a couple of functional groups in here. Can anybody identify any of the functional groups in the compound on the left? Absolutely. Well, thanks a lot, Ariana. Yeah, we get that one pretty quick. Okay, alcohol and a carboxylic acid. I would agree with you on that. Yes, so we have an alcohol here, right? I'm going to circle that carbon, and I mean this carbon here, because an alcohol has an R group attached to an OH, right? So this is an alcohol. Alcohol. And the other functional group that we have here is the carboxylic acid. So notice that we have the carbonyl, but attached, so this is the carbonyl, but attached to the carbonyl you have an OH, right? A hydroxyl is what we call that. And so together they make a carboxylic acid. So if we have R, something that looks like this, right? This is a carboxylic acid, so carboxylic acid. All right. What about the next one? Can anybody identify any functional groups in the one on the right? Yeah. So, oops, turn that down. Yeah, we have an ether. So we have an ether. I'll circle the ether first. So an ether is when we have an R group and then an oxygen. Oops. Then an oxygen and an R group. So this is an ether. Somebody else said an amine. Yes, there's an amine. So the amine is when we have an R group attached to an NH2 or something with a nitrogen on it. Yes, and the last one is an alkene. So we have a carbon-carbon double bond here. And so this one would be an alkene. Yeah, good. All right, let's keep going. So we've identified all the functional groups there. Let's try this one here, the one on the bottom left. Not my prettiest artwork with my Apple Pencil, but there's two functional groups in this one. Aromatic, yes, thanks, Hannah. Absolutely. There's an aromatic in this one. Yes, so we'll put that in here. Aromatic. And there's one other one. Yes, thanks, Pablo, the alkyne. Here we go. So this is our, so when we have a carbon with a triple bond on it, like that, so this is an alkyne. There we go. And the last one, let me just zoom out here. The last one, there's three functional groups in this one. Anybody identify any of them? Yeah, absolutely. We're definitely on the right page for sure. There's a sulfide. Yes, so this would be a sulfide. So when we have an R group, a sulfur, right, that's a sulfide. Yeah, any other ones? There's a couple more. Yeah, there's an amine, absolutely. So this one here, this would be an amine. So amine is when you have a nitrogen with R groups attached to it, okay? And the last one is a ketone, that's right. Absolutely, there's a ketone. I'm going to circle this whole thing like this because technically the ketone is when you have an R group with a carbonyl and then another R group attached to it. So this would be a ketone. There you go. So there's some practice in identifying functional groups. Are you going to have to work at it to master it and to really have all of them down pat? Absolutely. But remember, the importance of the functional group is that it enables us to predict some reactivity of the molecule. And we're going to look at extensively, we'll look at the chemistry of alkenes and alkynes later on in this class. So we'll look at a whole bunch of reactions towards the end of the class. All right, well, let's get back into our chapter 2 slides now that we've covered some of that. And we were just starting off on section 2.4. So remember, so far, anytime I drew a bond line structure, I didn't bring up formal charge whatsoever. However, we're going to look at plenty of bond line structures where we do, in fact, have formal charges. So let's follow along here. It says a carbon atom is going to have 4 bonds when it doesn't have a formal charge. However, if a carbon has a positive charge on it, then it adopts an sp2 hybridization, and it's only going to have 3 bonds. And so how would you tell the reader or the looker, in a way, the person who's looking at your bond line structure, that your carbon only has 3 bonds and therefore a positive charge, what we call a carbocation? Well, the way you do that is you actually put a positive charge next to that carbon. So if we look at this carbon here, the fact that somebody put a positive charge next to it, they actually wrote plus in a circle, it means that that carbon only has 3 bonds. There is no hydrogen attached there, right? And how do we calculate the formal charge, right? Formal charge is equal to the number of valence electrons minus sticks minus dots. And so since it's implied that there's only 3 sticks, we have 4 valence electrons for carbon minus 3 sticks minus 0 dots, and that gives us +1. And that is why we have a +1 charge for our carbocation. If you have any one of these carbons here that you have a positive charge next to, it's implied that we only have 3 bonds. So if we look at this carbon here, since we have a positive charge, the carbon must have 3 bonds, and therefore it's implied there's only 1 hydrogen. And this carbon on the end, it's implied that there must be 2 hydrogens in order for the carbon to adopt a positive charge. Give me a thumbs up if you follow me on the rationale, or are there any questions about that? sp2 hybridized carbon. Okay, good. Okay, with 3 single bonds, no double bonds, having a +1 charge. All right. So on top of carbocations, we're going to look at carbanions quite a bit as well. So a carbanion is a carbon that has 1, 2, 3 bonds, but it also has a lone pair of electrons. Right? And if we calculate the formal charge of the carbon in a carbanion, it's going to be 5 minus 3 sticks minus 2 dots, and that gives us -1. And that's why we put a -1 charge next to it. And so it's implied that the carbon is sp3 hybridized. It's got 4 regions of electron density. However, instead of being 4 bonds, it's got 3 bonds and 1 lone pair, and therefore it has a -1 charge. So carbocations and carbanions are things that we're going to see all the time moving forward in this class. So formal charge affects the stability and the reactivity of molecules, and so it's imperative that you can identify formal charges in a structure. If you take a look at this structure here on the bottom right, well, the only structure on the page, there's a bunch of formal charges that are missing. And what I'm going to do, just to make things easier since we're remote, is I'm going to highlight this oxygen in green, I'll highlight this one in yellow, and I'll highlight this one in, I don't know, red. Okay, so we'll start with just the oxygen atoms. Do any of these oxygen atoms have a formal charge? Could anybody identify the color of the oxygen and what its formal charge would be? I'll give you a clue. So there are some formal charges in here. Yeah. So somebody says the carbon in green has a +1 charge. I would agree with that. Right, the carbon in green does have a +1 charge. Why? Because we have 6 valence electrons for oxygen. Subtract 3 sticks minus 2 dots gives us +1. So yes, the oxygen in green has a positive charge. What about the oxygen in red? Does that have a charge? Thanks, Nikki. Absolutely. The oxygen in red has a -1 charge, right? If we take 6 minus 6 minus 1, so 6 dots minus 1 stick. I did it backwards here, but anyhow, you get a -1 charge. The oxygen in yellow has no formal charge because, right, exactly, because it has 2 bonds and 2 lone pairs. Let's try, there's one more formal charge in here. I'll highlight this nitrogen in green, okay? The one in the nitrogen in green has a formal charge. Could anybody identify what the formal charge is? We'll leave it at that. What is the formal charge? It's +1, right? Exactly. So the nitrogen in green has a +1 charge. And there you have it, folks. The other, the sulfur and the other nitrogen, they do not have formal charges. And so we've identified all the formal charges in this ion. So this would overall have a +1 charge, rather. There we go. So a little bit of formal charge work there. So, something that you've probably noticed me do is leave out lone pairs. In fact, I've done it a bunch of times in drawing structures with you. And this is a bad habit that I've gotten into after being an organic chemist for 20 years, because oftentimes organic chemists leave lone pairs out in their structures because we just assume that they are there, or it's implied that they are there. And if you mean, like, what do you mean by implied, Mr. Dion? Well, let's say I drew this anion here, okay, the one I have in the black circle. You see that you have a negative charge by the oxygen, and there's no lone pairs on it. But a good organic chemist can look at that and say, well, there must be 3 lone pairs on that oxygen. And how would they know that? Because in order for the oxygen to have a -1 charge, it has to have 3 lone pairs, right? Because if we take 6 minus 1 stick minus 6 dots, we get a -1. So it's implied that here there are 1, 2, 3 lone pairs. But again, I've looked at it so many times in my life that I'm used to seeing it with just a minus charge, and I know that there is not. I know that I can leave those electrons out. However, my students, one thing, I love learning things from my students. Learn great things from my students all the time. And if I can make a recommendation moving forward, is that sometimes I will leave lone pairs out, but I would recommend that you don't do it yet. Okay, you're learning the subject, don't do it yet. Take some time, make sure you know where all the lone pairs are before you start leaving them out. So my students, what they always used to say is, friends don't let friends leave lone pairs out. So we know that when oxygen has 3 lone pairs and 1 bond, it has a negative charge. And also something that you guys know very well from studying water enough times is that when oxygen has 2 bonds and 2 lone pairs, it's implied, we know that it has a neutral charge, or it has no charge. And therefore, if you draw an alcohol like this and you don't put the lone pairs in, it's acceptable, right? Because there's no charge on there. We know that there are 1, 2 lone pairs. It's implied that they are there. But again, since we're learning the subject, I recommend you include them. I'll just erase them for now. And then finally, when oxygen has 3 bonds and 1 lone pair, it has a +1 charge. And you would have seen that 1,000 times in the hydronium ion, right? When you draw hydronium, the oxygen has 1, 2, 3 bonds and 1 lone pair, right? And has a positive charge. And the same thing would apply to any oxygen that has 1, 2, 3 bonds and 1 lone pair. It has a +1 charge. And so again, it's implied that this oxygen here has 1 lone pair, but we can leave it out. But again, I recommend that you put in all the lone pairs in everything that you're drawing moving forward. So those are the possibilities for oxygen. Okay, so when oxygen has 3 lone pairs, 1 bond, it has a -1 charge. When it has 2 bonds, 2 lone pairs, it's neutral. And when it has 3 bonds and 1 lone pair, it has a +1 charge. What about nitrogen? It's another heteroatom that we're going to see a lot of. Well, going a little bit faster now, when the nitrogen has 2 bonds and 2 lone pairs, it has a -1 charge. So what does that mean? It's implied that if you see a nitrogen with a minus charge on it, that there are 1, 2 lone pairs on it. You need to be able to see that in your mind's eye. And since you probably can't at this point, that's why you should always draw them in. When nitrogen has 3 bonds and 1 lone pair, it's neutral. And when nitrogen has 4 bonds and no lone pairs, it has a +1 charge. Now, if I can encourage you, once you've gone through all the practice problems multiple times, you're going to know this stuff frontwards and backwards. You will have no question in your mind about how many lone pairs there are when you see a formal charge on an oxygen or a nitrogen. So with that in mind, let's get some practice here. It says draw all the lone pairs in on the oxygen. So let's say we were drawing the first compound. Okay, we have a -1. We have a -1 charge on the oxygen. And so how many lone pairs are missing on this oxygen? How many lone pairs do I need to scribble in here to give it a -1 charge? 3, absolutely. So 1, 2, 3 lone pairs. What about the next one? This compound is called pyran, or tetrahydropyran. It's the oxygen is neutral. So how many lone pairs must I draw in? 2, good. And the last one, the oxygen has a +1 charge, and therefore it's missing 1 lone pair. See how quick that is? Okay. Students usually master that concept pretty quickly. Now let's move on to talking about bond line structures in 3D. All right. So not only do molecules have, we draw molecules on paper, which is 2 dimensions, or the iPad screen, which is 2 dimensions. Something you're probably aware of by just looking at Vesper theory and general chemistry, and we looked at it a little bit yesterday, is that you know that molecules are not 2-dimensional, right? They have 3-dimensional structures that take up space in 3 dimensions. And so how do we represent, molecules in 3 dimensions when we're using a piece of paper or a screen? Well, the way that we do that is, let's say you have a compound like this one here. If you want to show that a bond is coming out of the screen or out of the page towards you, in that case, we use a wedge. So we call this thing here, we call this a wedge, right? And that's coming out of the paper. And if we want to show that a bond is going into the page, we use what's called a dash. Call this a dash. And that means that the bond is going back into the paper. And if you're wondering, well, hold on, Mr. Dion, what about all these other bonds? They're not wedges or dashes. No, those are in the plane of the actual paper or the screen, all right? So if we look at the next structure, you can see that the ring, everything here is in the plane of the screen or the page or the board or whatever. But you see that the alcohol on the left is on a dash, and so it's going into the page or the screen, and the alcohol on the right is coming out towards you. So we can say here, this is our dash, so this is going into the paper, or into the screen, maybe into the screen, and this one here is coming out of the screen. All right. And then this last one here, you have a bicyclic. And sometimes students can't wrap their heads around the bicyclic. It's usually good to make a model of a bicyclic, but what's being shown here is you have a 6-membered ring. So 1, 2, 3, 4, 5, 6, but you've got a bridge attaching carbons 2 and 5. So this is a carbon here. You call that carbon 7. It's kind of coming up over it like a little hat, so to speak. Anyhow, but that's coming out towards you, since the bonds between carbons 2 and 7 and 5 and 7 are wedges. So that means it's sticking up towards you. The bromine, of course, is coming out towards you. And this methyl group, this CH3 group, is going down. All right. There are other ways that we represent structures in 3 dimensions. Something that we're going to see a lot of when we study carbohydrates in Organic 2 is the Fischer projection. And the Fischer projection, we only use this for acyclic compounds. And the way the Fischer projection works is all the bonds that are vertical, so going straight up and down, those are all dashes, so they're all going back into the page. And anything that's horizontal is a wedge. And so if we have something that's horizontal like this, you can assume that all these are coming out towards you. And anything that's vertical, you assume it's a dash and it's going back into the page. The next one is a Haworth projection, or some people pronounce it a Haworth projection. So what's being shown here in this structure would be the same thing as if I drew a cyclohexane like this, and you have the OH group pointing up. So you would have it going up like this, and then not very pretty, OH like that. And then the bromine is going down into the page like that. So we kind of flip it on its end kind of thing, so that you can see the OH is clearly above the plane of the ring and the bromine is below the plane of the ring. We only use Haworth projections or Haworth projections for cyclic compounds. It's the only time you see them. And then bicyclic compounds. So this is a bridged compound here. And we'll talk more about bridged compounds later once we get into the nomenclature of alkanes. Now, there's an interesting, medically speaking, since we don't use pages in the electronic book, but there's an interesting, medically speaking, that I want you to take a look at that deals with how the 3-dimensional structure of a molecule can be very pertinent into its reactivity in the human body. In fact, you can take compounds that look almost identical, but just have a different arrangement of their atoms in 3 dimensions, and that can have very drastic effects. For example, one of the compounds might have the desired therapeutic effect, whereas the other one could be a poison. And so you have to be very careful about the shapes of molecules. All right, so that brings us to section 2.7, where we're starting to look at what is referred to as resonance. And this is going to be your initiation into drawing curved arrows. If you remember the very first slide or second slide I showed you, I had some curved arrows, and I said they represented the flow of electrons. Well, we're not going to talk about reactions yet. So we're not going to talk about bonds being broken and bonds being formed in a chemical reaction. However, what we're going to do is we're going to find a way to represent the fact that, or to demonstrate the fact that when we have compounds that have a formal charge with a pi bond or formal charges, is that these pi bonds or formal charges are often more spread out than a bond line structure can imply. And so what we're going to look at quite a bit is the allyl carbocation, and that's this guy right here. We call this an allyl carbocation. And what's interesting about this structure that I have in this yellow oval is that there's nothing wrong with it. Okay, everything is cool with this structure, for lack of a better way of putting it, but it doesn't adequately describe the allyl carbocation. Okay, there's nothing wrong with the bond line structure that's drawn here, but it is not a complete picture of the allyl carbocation. So if you're wondering, well, what do you mean by that? Well, let's take a look at this allyl carbocation structure first of all. It says there's a p orbital on carbon 1, 2, and 3. Now let's take a quick look at this. If I look at carbon 1, who could tell me what's the hybridization of carbon 1? And it's not a trick question. What's the hybridization of carbon number 1? It's sp2, right? Because it's got 2 bonds. So that means it's got 2 hydrogens. So it's got 3 sigma bonds and 1 pi. Therefore, it's sp2. Okay, so we've got that down. What about carbon number 2? What's its hybridization? No, it's not sp. It's got 3 bonds, right, that are shown, and there's one that's implied, right, because there's a hydrogen attached to it. Therefore, it's sp2, right? And then we have the carbocation on the end, right? And in order for the carbon to have a positive charge, it has to have 2 hydrogens, and therefore it's sp2. So every single carbon in the allyl carbocation is sp2 hybridized. So if I redraw the allyl carbocation here, like this, very carefully, what that means is I have a p orbital on this carbon because it's sp2. I have a p orbital on this carbon because it's sp2. And I have a p orbital on this carbon because it's sp2. Now, since I have 3 p orbitals in a row, what it does is they can all overlap with one another. And that creates like a tunnel or a conduit where the pi electrons, right, because these are pi electrons, those are in a pi bond, therefore they're pi electrons. Those pi electrons can be delocalized or not localized between carbons 1 and 2. Since they have all 3 of those p orbitals available to them, they can actually be delocalized over the entire allyl carbocation. And so again, the structure that we have shown here is not a complete representation of the allyl carbocation. Here's a picture that shows those 3 p orbitals, and it does a better job of showing how they are actually touching. They are actually overlapping with one another. And again, the word that I used was tunnel, but we can say it's a conduit. And so it enables those pi electrons to be delocalized or shared across all 3 of those p orbitals. And so when we look at the allyl carbocation, where we show the pi bond between carbons 1 and 2, it's not a complete accurate representation because those 2 pi electrons, these pi electrons or pi bond, whatever you want to call it, they are actually delocalized across all 3 orbitals. And if you're wondering, well, how in the heck do you show it then? How would you represent it? Great question. The way we do it is we draw 2 structures. We draw 2 structures instead of 1. We say, okay, well, this is one allyl carbocation, but we know that this pi bond could be between carbons 1 and 2, but it could also be drawn between carbons 2 and 3, because the reason I put those numbers in is because I'll always have a student say, well, Mr. Dion, all you did was flip that around. No, I didn't. What I'm doing is I'm showing the delocalization. What does delocalization mean? It means that these pi electrons in that blue line, okay, they are not localized between carbons 1 and 2. They're delocalized across the entire ion. They can be they could be drawn between carbons 1 and 2. Shoot, didn't mean to do that. They could be drawn between carbons 1 and 2, or they could be drawn between carbons 2 and 3. And then if you're thinking, well, is it just vibrating back and forth? No, it's not doing any such thing. Neither of these are a perfectly accurate representation of the allyl carbocation. What we do is we say the allyl carbocation is actually a hybrid of these 2 structures, right? What's a hybrid? It's a mixture of these 2 structures, but these 2 structures contribute to the resonance hybrid, okay? So if you're wondering, well, could you draw the hybrid? The answer is yeah, you can, but I don't ask my students to draw the hybrid. So if we draw the hybrid, the way we would do it is kind of like this, where we would say the pi electrons aren't localized between carbons 1 and 2 or 2 and 3. We draw a dashed line like this between all 3 carbons. I don't ask my students to draw that, okay? I don't ask my students to draw a resonance hybrid. However, if you look at the selected practice problems from chapter 2, I do have a couple of questions where, it asks you to draw a resonance hybrid because I think it's good practice. Okay, somebody says, how can you tell the difference between resonance structures and the molecule being turned in space? The way that you know that you're dealing with resonance structures is when you have an open square bracket and a closed square bracket and a resonance arrow. So this is an arrow that denotes resonance. We know that we are looking at a resonance structure. So if you don't draw the open and closed square brackets and don't put a resonance arrow, it's not correct. Okay, you have to have an open and closed square bracket and a resonance arrow. Also, be sure that you're using a resonance arrow. This is an arrow for resonance. If you draw an arrow like this is not a resonance arrow. This is an arrow for equilibrium, which you would have seen a lot of in general chemistry too, when you did a whole chapter on equilibrium. So there we go. So remember, these resonance structures that we see here, they are not switching back and forth. That is not what is happening. And the analogy that I have on the slide here is if you look at the hybrid, if you look at a nectarine is a hybrid of a peach and a plum. But it's not like you look at a nectarine 1 second and it's a peach and then you turn your head away and then you look back and it turned into a plum. No, it's a hybrid of both of those. And so what we say is we say this resonance contributor and this resonance contributor, they both contribute to the resonance hybrid, right? Together, they make up the resonance hybrid. Again, what we're trying to do is we're trying to show you something or draw something on paper that is complex. And it's not just it's not that simple that we can just draw one structure and say, this is it. We have to draw 2 structures and say both of these contribute to the resonance hybrid. All right. So it says delocalized electrons are spread out and thus lower energy. So what resonance does is it stabilizes a molecule. My good friend Dr. Diaz, what he likes to say is electrons are like hyperactive children, okay? If you give them room to move, they're going to do it, okay? If you give them room to move, they're going to do it. Electrons love to move. And so when you give them space to spread out over 3 atom centers instead of 2, that stabilizes the molecule or stabilizes the ion. So the delocalization of charge, again, is just the idea is that the charge is spread out over the molecule or the ion instead of being stuck on one carbon or the other. So what we're going to be doing now is looking at curved arrows that enable us to draw resonance structures. And you're going to have to strap your skates on here because I'm going to go over a few rules with you. But if there's one thing I've learned teaching science students is that science students usually like rules and then following those rules and then getting a good grade, right? So throughout organic chemistry, we're going to be using curved arrows to show electron movement. And when we have a curved arrow that has a double head on the end, that means that you're showing the movement of 2 electrons. Something that you're going to see in chapter 10 is a curved arrow where you have only 1 barb on it like that. That is what we call a fishhook arrow, and that shows the movement of 1 electron. We're not going to look at those at all. Okay, that will be saved for chapter 10, which is many, many weeks away. So right now, we're only going to be looking at arrows that show the flow or the movement of 2 electrons. That is it. So pairs of electrons. So the arrow starts where the electrons are currently located, and then they end up where they're going to be after the electrons are moved. Now, keep in mind, we're not looking at reactions yet. We haven't gotten there. Right now, when we're using curved arrows, we're only using them to show the delocalization of electrons. We're going to start looking at electron reactions in chapter 3. So that's for another class. Right now, we're just showing the delocalization of electrons, and therefore we're only using the curved arrows for resonance structures only. So before we take our next break, I want to make sure that we cover all of the rules for drawing curved arrows. Are you ready? Here we go. Here are the rules for drawing curved arrows. The first one is that when we're using curved arrows to show resonance, right? We're not doing reactions yet. is you never show a single bond, what we call a sigma bond. You never break a sigma bond, okay? You never show a sigma bond as being delocalized, because if you're actually breaking a sigma bond, that would be a chemical reaction. We are not talking about reactions. What are we talking about? Resonance. We're showing the delocalization of electrons. Reactions is for another day. So again, single bonds, those are what break in reactions. And we are not talking about reactions. We are talking about resonance today. Okay? So we're never going to break any single or sigma bonds. Resonance occurs for electrons existing in overlapping p orbitals, pi bonds or lone pairs, not sigma bonds. So we're always going to look for overlapping p orbitals in order to draw a resonance arrow. And if you're wondering, like, what do I mean? What do you mean by that? Well, we already saw in the allyl carbocation 3 p orbitals in a row. So we're always going to have some kind of situation like that. All right, let's move on to rule 2. It says never exceed an octet for the second row elements. Things like boron, carbon, nitrogen, oxygen, fluorine. These are in the second period of the periodic table. Ergo, they can never have more than an octet of electrons. That would be a very bad thing. So if we look at any of the arrows here, I love this slide, bad arrow, you know, it's scolding the arrow or something. But why is this arrow here? Why is it a bad arrow? Because if you were to draw the product of this, and don't do it because it's wrong, I'm just going to do it for demonstration purposes only. But if you were to do that, you end up with a carbon, right? So you take this oxygen. So the tail of the arrow is starting on the lone pair, and then the head is ending up between these two nuclei, the nucleus of the oxygen and the carbon. So that means you're forming a new bond between the oxygen and the carbon. So now you're going to have a double bond here like this. What do we call that? A Texas carbon, right? I shouldn't say that. But anyhow, we call that the Texas carbon, and that is a very bad thing. So that would exceed the octet for the carbon. We don't want to do that. You see the same thing is happening in the next arrow. We'd be exceeding the octet for the nitrogen here, for this oxygen here, and for this carbon here. So we would be exceeding the octet rule for all of these, and so they all violate rule number 2. To rehash, rule number 1 is when we're drawing resonance structures, we don't break sigma bonds. Rule number 2, we don't exceed the octet rule for carbon, oxygen, nitrogen, fluorine, or boron. All right. If you have a second row element, can it have less than an octet? Absolutely. And so if we look at this compound here, can we draw a resonance structure where we delocalize the pair of electrons in the pi bond between the carbon and the oxygen? Absolutely we can. Why can we do that? Let me ask you a question. This carbon that I have the arrow pointing towards, what is the hybridization of that carbon? Not a trick question. What's the hybridization of this carbon? A double bond and 2 singles. It is sp. sp2, yeah, sp2. And what's the hybridization of this oxygen with 2 bonds and 2 lone pairs, but one of the bonds is a pi bond, right? The hybridization of this oxygen, since it's got 3 regions of electron density, is also sp2. So what does that tell you? It tells you that both of those atoms, the carbon and the oxygen, right? The carbon has a p orbital on it, and so does the oxygen. So that means we have overlapping p orbitals, right? So if these 2 orbitals are touching each other, that means it forms like a tunnel or a conduit. And so the pi electrons can be delocalized. They can go up onto the oxygen. So if I draw this resonance structure, so I'm just going to erase all this so you can see it very clearly. When I move this pair of electrons from the pi bond onto the oxygen, now the oxygen adopts a negative charge, but the carbon has a positive charge, +1 and -1. They balance each other out. And so we have a neutral species. And so we can say that both of these, where's my eraser? We say both of these contribute to the overall resonance hybrid, right? How do we know this is a proper resonance structure? Because I have my open and closed square brackets, and I have my resonance arrow. All right, it says, in each of the following cases, determine whether the curved arrow violates either of the 2 rules and describe the violation, if there's any. Don't forget to count all hydrogen atoms. So let's take a look at the first one. I'll start by drawing an open bracket, put my resonance arrow, and I'm taking this pair of electrons from the pi bond and I'm moving them in between this carbon and blue and this nitrogen. So what am I going to end up with? I'll end up with something that looks like this, where I would have this hydrogen, and this methyl group here. What rule am I violating here? You can't have a nitrogen with 5 bonds. Thanks, Katana. Right? That is just totally wrong. Okay, so nitrogen exceeds octet. So therefore, bad arrow. All right. What about the next one? Is the next one a reasonable arrow? Yeah, there's nothing wrong with the next one at all. I have a negative charge on my oxygen, and now my carbon has 3 bonds, right? So it's going to have a positive charge, and so this one is good. There's nothing wrong with that resonance structure at all. And if I draw the next one, so I put my open bracket, draw my resonance arrow. So what am I going to do? I'm going to have this, and then I'm going to have a double bond here. So is there a problem with this one? Is there a problem with this one? I say there's a big problem with this one, okay? So this is where you've got to be Johnny on the spot with your bond line structures. How many hydrogens are attached to this carbon in the blue circle? There's 1 hydrogen attached here, right? Did it go anywhere? Nope. And so it's still there. And so the carbon is exceeding an octet, okay? So we'll put here bad arrow, carbon exceeds octet. And this is where you've got to really practice your bond line structure so it becomes second nature to you that this hydrogen was here all along and it didn't go anywhere, and therefore that would break the octet rule. All right, there you go. So again, it just takes a lot of practice with bond line structures to really master that concept. All right, let's see if we can draw some formal charges here when we draw our resonance structure. So it says when using curved arrows to show resonance structures oftentimes carry a formal charge. So I'm going to give you a second to try to draw the result of these 2 curved arrows. I'm going to try to give you a second to draw what you would get when you're done. What's the question mark? And could anybody tell me which atom is going to have a positive charge on it in here? Could anybody describe it to me in the chat, or unmute their mic and just yell it out? Which atom is going to have a positive charge on it? It's the oxygen, isn't it? Yeah, absolutely. Absolutely. The oxygen is going to have a positive charge, isn't it? So if we draw the result, we're going to have something. I'll start by drawing this kind of the skeleton. So we're going to have something that looks like this. So this first curved arrow that I have the black oval around, the head of that arrow is ending up between the oxygen and the carbon. And so I'm going to make a double bond there. I still have 1 lone pair. Right, Katana? And when we have 3 bonds and 1 lone pair on an oxygen, it has a positive 1 charge. Then the second curved arrow, this one here that I have in the blue circle, that curved arrow is starting on the pi electrons. Okay, technically it's starting on the pi electrons, so you could draw it touching the pi electrons, but whatever, that's neither here nor there. So now we're going to have this carbon, but it's going to have a lone pair on it. So what's the charge on the carbon that I have highlighted in yellow? What's this charge going to be? It's going to be -1. Why is it -1? Because there's already a proton there, right? So it's got 3 bonds in 1 lone pair, and therefore it has a -1 charge. And so that would be the resonance contributor, or the second resonance contributor. So again, we say that both of these contribute to the resonance hybrid. All right, we say they're both contributors to the resonance hybrid. All right, so let's do the next section before we take another break, which deals with resonance pattern recognition. Now, this is put forth by the author of our textbook, David Klein. So Klein is the most popular textbook, organic chemistry textbook in all of America. So I tend to think that David Klein knows what he's talking about. And he developed these, or kind of highlights these 5 general bonding patterns that you can use to identify resonance or help you identify resonance structures and when they occur. All right, so you can memorize these. That's one thing you could do. It might be good to memorize them at the beginning, but as you move forward in the course, you're going to get used to drawing resonance structure after resonance structure, so on and so forth. So eventually get pretty used to it, and you won't really have to refer back to these. But for now, they will work. So the first one is an allylic lone pair. So first, if you're wondering, what does allylic mean? So, if we have a double bond, okay, so here's a double bond. The positions of the carbons that are part of the double bond, we say these are vinylic positions, okay? But if you go one atom away from a double bond, so one atom away from a double bond, we call this a vinylic position. So vinylic position, all right? Did I say vinylic when I meant allylic? Jeepers. I think I need more coffee. So one atom away from the vinylic carbon, we call that an allylic carbon. All right. So an allylic lone pair is one. So you can see that here we have a double bond, and one atom away on the oxygen, we have lone pairs. So that's an allylic lone pair. The next one is an allylic carbocation. So if we have an allylic carbon, so again, here we have a double bond, one atom away, we have a positive charge, so that's what we call an allylic carbocation. The next one is a lone pair a lone pair of electrons adjacent to a carbocation. We see that here we have a lone pair right next door to a positive charge, so that will be a possible resonance structure. The next one is a pi bond between two atoms of different electronegativities. If you have a pi bond between carbon and oxygen, they have differing electronegativities. Carbon's is 2.5, oxygen's is 3.5. So therefore, we can have a resonance structure there. And the last one is a conjugated pi bond. So remember, I told you that conjugated means you have double, single, double, single, double, single alternating. So like in the aromatic ring, right? It goes double bond, single bond, double bond, single bond, double bond, single bond, so on and so forth. And so in that case, you can draw resonance structures for those as well. So those are the 5 general bonding patterns that we find when we have resonance. So let's go back through this. So I told you what a vinylic position was and an allylic position was. The carbons or the atoms involved directly in the double bond, those are called vinylic positions. So these would be vinylic carbons. If you go one atom away, okay, one atom away, here, 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 and here, these would be allylic positions. So if we have an allylic lone pair, so let's take a look at this molecule. If we have this double bond, right, it's a beautiful double bond, we go one atom away. So one atom away would be this nitrogen. There's a lone pair on it, so that's an allylic lone pair. If we go another atom away to this carbon, there's no lone pair on it. Ergo, it is not, or it does not possess an allylic lone pair. And so if you have an allylic lone pair, you can draw a resonance structure for that. So if we take a look at each one of these structures, they all have allylic lone pairs. And when you have an allylic lone pair, you must draw two curved arrows in order to show the delocalization of that allylic lone pair. And so what we're going to do now is we're going to draw an open bracket for each one of these, and we're going to get some practice on drawing the resonance structures for each one of these compounds or ions. So I'll put a resonance arrow. Normally, we don't draw resonance structures vertically like this, but just in the interest of space, we'll do it like this. Okay, so let's take a look. The first one, the one on the far left, let me fix this arrow here, can make it a little prettier. There we go. If we look at this first one on the far left, we would take the lone pair and we would make a new pi bond here. That would break the octet rule of this carbon. And so we're going to take this pair of electrons and we're going to move it onto this carbon here. So our new resonance structure is going to look like this. We're going to have the pi bond over here, and we'll have moved the negative charge like this. With the next one, we again have an allylic lone pair, right? How do I know that? Here's my pi bond. I go one atom away, and I have a lone pair of electrons. And therefore, I can draw a curved arrow, 2 curved arrows as a matter of fact, where I show the delocalization of the lone pair to make a new pi bond. That would break the octet rule of this carbon, so I can't just leave it like that. I have to take the pi electrons and move them onto the carbon next door. And so I'm going to draw my new resonance contributor. I have a lone pair here, therefore a negative charge. I have an oxygen with 3 bonds in a lone pair, so it's got a positive charge like this. So what we'll do now is we'll take a short break, and I'll give you a chance to draw the resonance contributors for each one of these. And then we're going to get into more details on resonance pattern recognition. So we're going to talk more about allylic lone pairs, allylic carbocations, lone pairs adjacent to carbocations, pi bonds between 2 atoms of differing electronegativity, and then we'll get into more detail on conjugated pi bonds in a ring. After we get through all that, then what we're going to do is we're going to take a look at all the different resonance contributors to the hybrid, and we're going to look at a set of rules that enables us to identify which contributors are going to contribute the most to the resonance hybrid. So there's a little set of rules that we look at here. It doesn't take too long to cover all that, but it enables us to evaluate our resonance contributors and identify which ones contribute most to the resonance hybrid. Then we're going to talk about the resonance hybrid a little bit more, and that brings us to almost the end of the chapter, where we talk about amides and the hybridization of the nitrogen in an amide.